Okay, so in this video here, we're going to look at some examples dealing with the operational amplifiers that we saw in the previous video. So the main purpose of this video is going to be able to look at the circuit, identify what kind of amplifier it is, and then answer whatever the question is here. So let's take a look at this, and again, at any point you might want to pause the video so that you can take the time to sketch out your circuit diagram and write down any question you might have here. So let's go ahead and start this problem here. So if I look at this circuit diagram, hopefully it doesn't take us too long to recognize that this circuit is a non-inverting amplifier. So once I've identified what the type of amplifier it is, the next thing I always do is, okay, well then let's write down the formula that I know for this. So the formula for the gain here is that the Vout is equal to 1 plus R2 over R1 times Vn. So I'm going to write that down now, and then I'm going to turn my attention to what the question is. So the question here is, what is Vout? Okay, well that makes it actually pretty simple here. So I just want to find Vout. Well, I've got an equation sitting here, and we can clearly see from this that R2 is 10 kilo ohms, R1 is 4 kilo ohms, and Vn is 4 volts. So now I just do an equation plug and chug and say that Vout then is going to be 1 plus 10k over 4k times 4 volts, and just taking a couple steps here just to make sure that we don't make any silly arithmetic mistakes here. We would have, I can't pull my calculator here. Vout is equal to 1 plus 2.5 times 4 volts, which of course is just 3.5 times 4 volts. So we have 3.5 times 4, which of course is 14 volts. Now before I say that Vout here is 14 volts, before I circle this as my final answer, I want to say, does this make sense? Well, look at the power supply. We have plus or minus 24 volts as our power supply, so can I obtain 14 volts as my output voltage? Well, of course, because it's less than the 24. We know here, maybe I should put it in red here, we know that Vout has to be between positive and negative 24 volts. And clearly 14 is, so we're fine. Now, if it wasn't, we again know from the previous lessons that means the op-amp has railed or saturated. Okay. Let's move on to the next example. Now for all of these I've already drawn the circuit out just to save some time in the video. So again, you might want to pause the video to draw the circuit here. Now the first thing here is, let's again identify the type of amplifier this is. I'm just going to make sure that this is clear, that this is the negative terminal there. Now if I look here, I can see that the input is tied to the negative terminal through this 10k ohm, and then I got a 3k ohm, and then I've got this load attached, which is something different than we normally have. But if I just look at the way these resistors are configured, I can see that this is an inverting op-amp. And we know here that the gain for an inverting op-amp, or my equation, is that Vout is R2 over R1. There's a negative there. It's inverting. Let me redraw that. Negative R2 over R1 times Vn. Now, we don't have any voltage supply here, so if we don't have any voltage supply here, we can assume that we have, quote, plus infinity volts and minus infinity volts. If they don't give you any power supply on a circuit diagram, that's what you can see, which of course is an invalid assumption. You can't get an infinite voltage. But essentially what we're assuming is that we have a power supply that's large enough to amplify the circuit, do the amplification that's present in the circuit without saturating the op-amp. So we're just assuming automatically we have enough voltage applied. Now, let's look at the questions here. So this is my equation for V out times V in. The first question, though, is what should R3 be? Well, that doesn't really have anything to do with V out over V in, or V out and V in. But R3 here is this resistor on the positive terminal. And remember, for our good practice, we said that R3 should be R1 in parallel with R2. Because again, it's for that input offset voltage. And well, that would mean I'd have a 2K ohm in parallel with a 3K ohm, which if I do that computation, that's not too difficult. That's just 2K times 3K over 2K plus 3K, which gives you 1.2 kilo ohms. So this should be a 1.2 kilo ohm resistor that we attach to the positive terminal. Now part B here, or the next part here, it says if Vn is negative 12 volts, what is the power across the load? That should be a question mark. And so it's wanting to know what's the power being dissipated across the load. Well, the load is this 10 kilo ohm resistor. So to compute power, we know of course power is equal to current times voltage, but again, because this is a resistor, we could do I squared times R, or we could do V squared divided by R. Now, one thing I want to emphasize is if you're talking about an output here, you never can determine what the output current of this op-amp is directly. And what I mean that by directly here, we can't just assume that, oh, it's 1 milliamp coming out, or we can't do a simple computation. We could eventually figure it out, but what we want instead here is we're going to want to know what the voltages are. Now, I didn't apply anything here, I didn't label anything, and I did that on purpose because we should be able to recognize that right here, if I put a little terminal here, that this voltage right here that I'd measure would be the output voltage. That's clearly the output of the op-amp. Well then, to compute the power, I'm just going to do voltage squared divided by resistance. And so what I'll do here is I'll say, well, okay, V out is negative R2 over R1, so that's negative 3K over 2K times the input voltage is negative 2 volts. And if I get that here, should be 3 volts, but let me just double check my arithmetic. Yes, we get positive 3 volts as the output voltage. But then the power across my load would be my output voltage squared divided by the load resistance, which would be 3 volts squared divided by 10 kilo ohms. And so if I do that, whoops, 3 squared divided by 10 kilo ohms, we get mine's already set in engineering notation, 900 microwatts, or you might write this as 0.9 milliwatts is what we're going to be getting as far as the power dissipated across the load. So we're not always going to just be asking for what's the output voltage. We could be asking for what's the power across the load. But again, it's really not a difficult problem. It's just a couple steps here. Alright, so we're going to look at one more example problem here. And again, we're going to see what the question is here, but before we even look at the question, we want to identify the type of amplifier this is. And looking at this, this would be a difference amplifier. And the output equation for this was that Vout was, here I've been writing these in red, that Vout is R2 over R1 times, and I'm going to emphasize it here, instead of doing V2 minus 1, V at the positive terminal, well, I should be careful here. I'll still do V2 minus V1, where this is, I'll put it here, this is going into positive, and this is going into negative. And why did I not just do V plus and V negative? Because V plus and V negative are actually these voltages right here, and they're the same. Because that's one of our assumptions for ideal op-amps. So V2 and V1, those are the voltages kind of going into the op-amp. All right. So now let's look at the question here. It says if V1 is 2 volts, okay, so I'm just going to go ahead and erase some of these things here. Put it into here. So I got 2 volts here. V2 is 4 volts. What should R1 be so that Vout is 6 volts? So I have Vout is 6 volts. And I'm just labeling my circuit, and clearly now, just labeling my circuit with all the information, I should see that this is a really easy problem again to do, because all I need to do is figure out what R1 needs to be, and I've got a very simple equation, and I'm just going to write down here, well, Vout I know is 6 volts, and this has got to be R2, which is 10 kilo ohms, divided by R1 times V2, which is 4 volts, minus 2 volts. And so then just doing some arithmetic here, we'd get 3 is equal to 10 kilo ohms over R1, because 4 minus 2 is 2, and dividing both sides by 2, of course, we'd get 3. And then flipping, we get R1 is equal to 10 kilo ohms divided by 3. And if we do that, it's not 3 volts, it's actually 3. It's unitless at this point. And if we do that, we get R1 is, of course, roughly 3.33 kilo ohms is what we'd need in order to get those appropriate voltages. So again, sometimes we're needing to determine what the resistor value is in order to go there. And again, why we want to do that? Well, I always like to look at things as far as debugging circuits. And sometimes, as silly as it might seem, is that sometimes there can be a wrong resistor value in there. Now, oftentimes the way you identify a wrong resistor value is either using the color code on the bars on it, or if it's a chip resistor, there's a number written on it which tells you what the resistance is. And I've actually seen production lines before. Now they have standards in place that this really shouldn't happen, but I've seen it happen once before where they were putting the wrong component in for the assembly of the boards. For instance, I don't precisely remember what the component was or the value was, but for instance, it was like they were putting a 1 kilo ohm resistor in when they should have been putting a 10 kilo ohm resistor. And of course, this is on a big, like high-speed manufacturing line and everything. And obviously that was a big deal because all their boards then suddenly didn't work because they had the wrong resistor values in. So knowing what the resistor value should be to then being able to go back and check is also something that's useful for us to be able to do. All right, now as I end this video here, these are the current op-amp circuits that we're going to look at, but there are more op-amp circuits to look at. I just want to emphasize that there are more op-amp circuits to look at, and I'm just going to draw a couple here. And the reason we're not looking at them quite yet is because we haven't gotten to these components. This is an op-amp circuit. And then you have another one where you have an op-amp circuit that looks like this. And one more here that I'll draw for you. Now I'm not labeling them, but these are all different types of op-amp circuits. This one here is what's called an integrator, which actually is in reference to that it's actually doing calculus. It's doing something called an integral. This is called a differentiator. And for the same reason, because this can do the calculus operation of taking derivatives. And then this one here doesn't look like it's anything, because you might say that there's no input voltage. And you're right, there's no input voltage, but remember, we have power supply voltages here. And believe it or not, this simple circuit, choosing appropriate values for R1, R2, and stuff like that. I know I haven't labeled, but choosing appropriate values for these resistors and capacitors, this is actually a square wave generator. You can generate a square wave out of this. And you can actually generate it at a specific frequency, and so you can actually generate a signal that looks like a square wave here, just like this, coming off of this op-amp. So there's lots of different circuits, op-amp circuits, and this still doesn't even cover them all here. So lots of different applications, lots of different ones. We will get into some of the more advanced applications and some of these things like integrator, differentiator, and the square wave generator once we've learned a little bit more about capacitors and inductors, which is quite frankly great place to end this video, because that's our next topic of discussion. We're wrapping up our discussion on op-amps, but when I say wrapping it up, it's only somewhat wrapping it up, because we're going to still have these come back in some of the circuits. As we said, once we deal with capacitors here and inductors, these circuits are going to come back, these op-amp circuits, so that we can see what is going on.